Imagine you're like a nurse standing in this incredibly busy hospital room and you're holding an IV bag.
Right, and you've got just a few seconds to calculate a dilution.
Exactly. I
Yeah.
mean, if you get it right, the medication works perfectly. But if you misplace a decimal or swap a step, it could literally be the end of a patient's life.
It's intense
Hmm.
because what you're doing in that high-pressure moment isn't just following some hospital protocol. You're actually performing this ancient mathematical ritual that dates back like 3,500 years.
Which is just mind-blowing. And welcome to the deep dive, everyone. Our mission today is to decode solving linear equations.
Specifically, we're looking at single variable multi-step equations, right? Like the ones you see on the TEAS and HESI nursing entrance exams.
Yeah, and we have this really fascinating stack of sources today. We're diving into everything from ancient mathematical texts to like modern cognitive psychology.
All to understand why something as basic as finding x is treated as this critical patient safety skill.
Mm.
Because, when you look at how these nursing exams are structured, they don't treat algebra as just some abstract classroom exercise.
Right, it's a proxy for clinical competence.
Exactly. So we're going to explore the cognitive traps that consistently cause, incredibly smart people to just freeze up on these tests. We'll look at the actual mechanics of how to navigate them and how humanity even developed the tools to solve these problems in the first place.
Okay, so before we start moving numbers around and doing the math, let's just get a plain English definition on the table.
Good idea.
The textbooks define a linear equation in one variable as a statement asserting that two expressions are equal, where the unknown quantity only appears to the first power. But, what does that actually look like if you're trying to visualize it?
Well, in plain English, we are basically looking at a seesaw. Both sides of the board have to weigh the exact same amount.
Okay, a seesaw, I can picture that.
Right. And sitting somewhere on that seesaw is a mystery box. That's Rx. And it doesn't have any strange properties. It's not x squared. It's not trapped under a square root symbol. And it's not, like, fluctuating down to the denominator of a fraction.
Right, it's just a plain old box.
Exactly. And the entire goal is to clear off all the extra weights on the seesaw until that one mystery box is sitting completely by itself.
So we can finally see exactly what it weighs.
Right. You just strip away the extra layers until the unknown is isolated.
Which sounds super tidy. But looking at our sources, humanity actually struggled for millennia to figure out how to do this efficiently, right?
Oh, absolutely. It's so easy for us to take the modern mathematical setup for granted. But for most of human history, I'm talking roughly from 1650 BCE all the way up to, like, the 1500 CE, there was no symbolic equation at all.
Wait, really? No symbols for thousands of years?
None. They practiced something called rhetorical algebra. So if you had a problem that we would quickly jot down today as, say, 3x plus 5 equals 20, ancient mathematicians wrote it out entirely in prose.
It was essentially just a giant word problem, because I saw an example from one ancient text translated as a quantity, its third part is added to it, it becomes 20.
Yeah, exactly.
And that feels less like math and more like a riddle a troll asks you before you can cross a bridge. How did they even solve something like that without symbols or variables?
Well, they used a method called the rule of false position, which is heavily documented in the Rhind Mathematical Papyrus. That's an Egyptian document copied around 1650 BCE.
Okay.
And instead of balancing an equation, they would just make a highly educated guess.
Let's test this on you listening right now. How would guessing actually solve a complex equation?
So let's say the riddle is a quantity plus its half equals 15. The ancient scribe would just say, well, I guess the quantity is 4.
Okay, but 4 plus its half, which is 2, equals 6. And the target is 15, not 6.
True. But the scribe would notice that 15 is exactly 2.5 times bigger than 6.
Oh, I see where this is going.
Right. So they simply take their original guess of 4, multiply it by 2.5, and they get 10. And 10 plus its half is 15.
Wow. They solved it purely through proportional scaling, just completely bypassing the need for an x or a formal equation.
Yeah, it's a remarkably clever workaround. But, eventually we did get variables and structured equations. And that brings us to the 9th century in Baghdad.
Ah, the House of Wisdom.
Exactly. A Persian mathematician named Muhammad ibn Musa al-Khwarizmi wrote a text around 820 CE. And what's cool is he wasn't writing for abstract academics.
Right, it was super practical.
Very. He was writing a manual for land surveying, commercial contracts, dividing complex inheritances. He called it the compendious book on calculation by completion and balancing.
And the Arabic word he used for completion was aljab, which is, of course, where we get the modern word algebra.
Right, and aljog referred to a specific physical move. If you had a subtracted or like a broken term on one side of your equation, you moved it to the other side to make it positive.
So you were completing it
Yeah,
or restoring it.
exactly. And the second crucial concept was almukabala, meaning balancing. So, canceling equal terms from both sides of the seesaw so it doesn't tip.
Okay, wait, I have to bring up the most fascinating detail from this historical timeline in our sources. Because when the word aljarb traveled to medieval Spain and Italy, it didn't just mean a mathematician.
No, it didn't.
An algebrista was the actual title for a bone setter.
Literally a medical practitioner who restores a dislocated or fractured bone.
I mean, that is just both the math sense and the medical sense meant restoring something to wholeness. You're fixing a fracture in the logic to reveal the underlying truth.
It's a really beautiful analogy, especially for nursing candidates studying this material today.
Totally. But to do that today, we rely on a symbol that Al-Khwarizmi didn't even have, right? The equal sign.
The fulcrum of our seesaw.
Yeah. The sources mention it was invented in 1557 by this Welsh mathematician named Robert Record, because before him, people just wasted so much time writing out the words is equal to.
Over and over again.
Right. And he chose two parallel horizontal lines for the most charming reason. He wrote that he chose them because no two things can be more equal.
It's brilliant in its simplicity, honestly. And it is the perfect bridge into how we actually manipulate these symbols today.
Because the entire foundation of linear equations rests on the principle those two lines represent. Whatever you do to one side of the seesaw, you must do identically to the other.
Right. Otherwise, the statement breaks and it's just no longer true.
So if you're facing a multi-step equation on the TEAS exam, the goal is to carefully strip away everything surrounding x. Let's talk about where people actually stumble when they do this.
Yeah, let's get into the mechanics.
The sources point to the distributive property as a massive trap.
Oh, it really is. Let's visualize one. Say you have a 4 outside a set of parentheses, and inside the parentheses is 2x minus 1. The first step is to distribute, right? To multiply that outside 4 by the terms inside.
So the left side should become 8x minus 4.
Exactly. But math education research shows that one of the most frequently documented errors is test takers forgetting to multiply that second term.
So they'll write 8x minus 1.
Yep.
Why does our brain drop the ball on that second number?
Honestly, it comes down to cognitive load. Under the pressure of a timed test, your brain just gets tunnel vision. You see the 4, you see the 2x, you multiply them to get 8x, and your brain instantly feels this huge sense of completion.
Oh, so you just check the mental box and move on.
Right, completely ignoring the -1 sitting right next to it. And the problem is, once you set that bone crooked, no amount of perfect math afterward will get you the right answer.
Okay, so the rule for you listening. Distribute to every single term inside the house, not just the one standing at the front door.
I like that.
Now, what about the order of operations? If we have an equation like, say, x divided by 4 plus 7 equals 19, if I think back to grade school, I remember PEMDAS, parentheses, exponents, multiplication, division, addition, subtraction.
The classic.
Right. So doesn't division come before addition and subtraction?
Well, here's the thing. PEMDAS is the rule for building an expression. It dictates how you evaluate a mathematical statement that is already fully assembled.
Okay.
But when you're solving an equation, you're dismantling it. You're taking it apart to find the mystery box buried inside.
So if getting dressed in the morning, putting on your socks, and then your shoes is PEMDAS, then taking them off at the end of the day requires reverse PEMDAS.
That's exactly it.
Because you cannot take your socks off until you remove your shoes.
Right, you have to peel the layers from the outside in. So in your example, x divided by 4 plus 7 equals 19. The addition of 7 is the shoe. The division by 4 is the sock.
Whoa, okay.
You must undo the addition first by subtracting 7 from both sides. Only then can you undo the division by multiplying both sides by 4.
So if the rules of the seesaw and reverse PEMDAS are this straightforward, why do nursing candidates, people who are mastering like complex biology and pharmacology, why do they freeze up when they see these equations?
It is a massive cognitive trap. There's this landmark study by a researcher named Erlwanger, and it was later expanded on by scholars like Knuth and Stevens. They looked at how our brains fundamentally interpret mathematical symbols.
And what did they find?
They found that a huge portion of the population views the equal sign operationally rather than relationally.
Let's actually test this on you, the listener. If I give you this simple sequence, 8 plus 4 equals blank plus 5, what number instantly pops into your head to fill in that blank?
For most people, the brain just screams 12.
Right, because your eyes track left to right, you see 8 plus 4, you see the equal sign, and your brain treats it like the enter button on a calculator.
Exactly. It just means, and now compute the answer.
But if you put 12 in that blank, the equation becomes 12 plus 5, which is 17, and 12 does not equal 17. The seesaw just tipped over.
It totally crashed.
Yeah.
The correct answer is 7, because 8 plus 4 is 12 and 7 plus 5 is 12. Both sides balance perfectly.
So this faulty mental model, treating the equal sign as a compute button rather than a statement of balance, is that the root cause of these errors?
It's the root cause of almost all multi-step equation errors.
Yeah.
If you don't truly internalize that the equal sign means the two sides hold the same weight, you will start making illegal moves.
Like what?
Like you'll subtract a number from the left side just to get x alone, but you don't do it to the right side because your brain is just trying to force an answer to appear.
Man, if our brains are naturally hardwired by calculators to misread the equal sign, how on earth are educators supposed to fight that? Because that question actually sparked a massive pedagogical conflict in the 1990s, didn't it?
Oh yeah, the math wars.
Yeah.
The National Council of Teachers of Mathematics, or NCTM, released these new standards that just ignited a huge debate over how to teach algebra.
And it's split into two distinct philosophies, right?
Right.
The traditionalists and the reform advocates. Keeping in mind that our sources present both sides impartially, let's look at why they clashed.
Sure.
The traditionalists favored automatic procedural mastery.
Right. They championed the flowchart method, or like the change sign algorithm. You just memorize the physical steps to isolate x. It is highly structured and incredibly fast.
Which makes sense. For a nursing student staring at a ticking clock on the TEAS exam, procedural fluency is a lifesaver. You don't have to ponder the philosophy of the math, you just execute the algorithm and get the answer.
But the reform advocates argued that speed comes at a dangerous cost. They pushed for the balanced model.
Okay, and what was their argument?
The reformers argued that if you only teach rote procedure without conceptual understanding, students become really brittle.
Brittle.
Yeah, like they might be able to manipulate symbols quickly when the equation looks exactly like the textbook. But the second a problem is phrased slightly differently or contains messy fractions, they panic.
Because they don't actually understand why the algorithm works.
Exactly. The balanced model forces students to visualize the seesaw every single time, which builds conceptual resilience.
Well, both methods arrive at the correct answer. One prioritizes speed and efficiency, while the other prioritizes robust understanding. And depending on whether you're racing a timer or verifying a complex drug dosage, both have deep value.
They really do. And regardless of which method you lean toward, there are a couple of universal misconceptions we need to clear up for anyone tackling these exams.
We already covered the biggest one. Only applying an operation to one side of the equation.
Yeah, the seesaw breaker. Another huge trap is a negative sign sitting in front of a set of parentheses. People frequently assume it only applies to that first term inside.
But distributing a negative affects every single term inside the parentheses. It flips all their signs.
Right. If you miss that, you've completely fractured the equation.
And then there's, like, the ultimate confidence killer, the messy answer.
Oh, yes.
We are so conditioned by grade school math to expect clean, whole numbers. When someone solves an equation and gets a negative fraction or a long decimal, their immediate thought is, I must have messed up.
But linear equations in the real world routinely produce messy fractions. A weird decimal isn't evidence of an error.
So what should you do?
The only way to know if your answer is correct is to take that messy number, substitute it back into the original equation in place of x, and see if the two sides of the seesaw actually balance.
Which brings us right back to the hospital floor. Why do the TEAS and HESI A2 exams care so deeply about this specific mathematical skill?
Well, medication error research continually flags calculation mistakes as a primary source of preventable harm in clinical settings. We're talking about misplaced decimals, incorrect unit conversions, and faulty dosage equations.
Let's visualize this with a concrete clinical scenario from our sources. Picture that IV bag we talked about at the very beginning.
Yeah.
You are told the final IV solution must contain exactly 130 milliliters of fluid.
Okay, so that 130 is our target weight on the right side of the seesaw.
Right, and you look at the instructions, and they require you to add a 40 milliliter shot of active medication into the bag. The rest of the volume needs to be a base saline solution.
Got it.
But the saline comes in a specific concentration that makes up 90% of the required base volume. So you need to find out how much of that base solution to actually pull into the syringe.
Okay, so we have an unknown base volume, that is
Yeah.
our x.
Yeah.
And the saline is 90% of that volume, so we write that as 0.9 times x.
Then we add the 40 milliliter medication shot. So the left side of the seesaw is 0.9x plus 40, and the right side is the 130 milliliter total.
Now, step back from all the clinical vocabulary for a second. Just strip away the saline, the IV bag, the syringe. What do you actually have?
0.9x plus 40 equals 130. It's just a coefficient times an unknown plus a constant.
Right. It is the exact same bone-setting logic Al-Khwarizmi documented.
And you dismantle it using the exact same reverse PEMDAS imbalance properties.
Exactly. You take off the shoe first. You subtract the 40 milliliter medication volume from both sides.
Which our brain can easily visualize, right? We know the bag is 130 total. We drop in the 4 milliliter shot, which leaves 90 milliliters of space left to fill. So mathematically, 0.9x equals 90.
And now you take off the sock. You undo the multiplication by dividing both sides by 0.9.
90 divided by 0.9 gives us an x of 100. So the unknown base volume is 100 milliliters.
You've restored the balance. You've correctly prepared the IV.
Right.
And, the exams test this heavily because they're measuring a proxy competency.
Right. They want to know if you can reliably manipulate these logical structures under pressure.
When the variables aren't just ink on a page, but an actual patient's well-being.
Okay, so let's distill all of this into the 5 core exam-style takeaways for you to just keep in your back pocket as you study. Number 1, an equation is a seesaw. Any operation you perform on one side, you must perform identically on the other side, or the equality shatters.
Spot on. And number 2, when facing multi-step equations, distribute first, combine your like terms second, and isolate the variable last. And please, when you distribute across parentheses, do not let your brain drop that second term.
Yes, remember the cognitive load trap. Number 3, use reverse PEMDAS. When you are dismantling an expression to isolate x, undo the addition and subtraction before you undo the multiplication and division. Shoes, then socks.
Love that. Number 4, embrace the mess. Decimal, fractional, and negative answers are perfectly normal. Just verify them by substituting them back into the original equation rather than, panicking over how they look.
And finally, number 5. The equal sign means balance. It means the two sides hold the exact same relational value. It is not a calculator command telling you to compute left to right.
Keeping these 5 principles centered will really move you from just memorizing arbitrary steps to actually understanding the mechanics of the math.
But before we wrap up, there is one final, incredibly thought-provoking point tucked away in our sources about where linear models fail in the real world.
Yeah, this is so important. Because the danger isn't just making an arithmetic mistake inside a linear equation. The profound danger is treating a complex situation as if it were linear when it isn't.
Wait, what do you mean by that?
Well, we spend years training our brains to view the world through perfectly balanced proportional equations, right? If I double the input, I get double the output.
Right.
If I cut the dose in half, the effect is cut in half. And we love the comfort and precision of that predictability.
But human biology is rarely perfectly linear.
Exactly. So the challenge isn't just knowing how to solve the equation. The real challenge for a clinician is recognizing when a patient's medical condition just stops acting linearly.
Oh, wow. Like, what happens when doubling the dose doesn't double the effect, but instead triggers a completely disproportionate systemic reaction?
Right. It forces us to ask, how do you recognize when the seesaw is simply no longer the right tool for reality?
That is heavy. It really forces us to remember that while math is the best tool we have to model the world, it isn't the world itself.
So true.
When you're sitting in a classroom, the precision of a textbook equation is comforting. But when you step out of the classroom and into the clinic, that math becomes just the baseline for navigating a totally unpredictable reality.
You're not just solving for X anymore.
You're setting the bone. You're making sure that when the stakes are at their absolute highest, the logic actually holds up. Thanks for joining us on this deep dive. We'll catch you next time.